Okay, so the list is getting shorter. Homework 9 was due today, which must mean you only have 3 more homeworks left. We'll finish lab 4 this Friday, and it will be due the following week, which is the April 16th. That's when the quiz will be. And then there will be no lab the last week of class. I will take 1 lab late, 1 week's worth of lab late for credit. So if you didn't turn in lab 1, you can email it to me and I will accept it. They have to come to me, not to a lab TA, because I've had people do this thing where they turn in 1 lab to 1 lab TA, another lab to another lab TA, and a 3rd lab to me, and try to get credit for the entire semester. Okay, but I will take 1 week's worth of lab, and that will improve your lab grade. Also, the course evaluations are available online. That is worth points on your final exam. And also, if I give you a final exam exemption, part of that is, yeah, if it's really bad, just send it to me. I'll take a look at it and I'll regrade it. I'll do that this semester. So, okay. So filling out the course evaluation is worth some points on the final. There's also a practice final that's worth points on the final. Those are exam points. They're more valuable than other points. And there'll be some bonus points on the homeworks, on the last few homeworks. There'll be like 120 points possible, and it's all still scored out of 100. So that can help pull your homework grade up too. Other than that, I do tend to, in this class, the grades do get curved slightly. It doesn't necessarily take a 90.0% to get an A, especially this semester. It's not that bad. I don't even want to show the slide. Cryptography, we don't know what's going on. We don't know who's teaching it. Embedded mixed signal design, still up in the air, will be taught by me. We do know that EE389 device physics is a good class if you want to understand how the individual transistors work on a deeper level. That will be taught by Daphne Chen. And we're hoping to get 490 back. I think it finally, last version of my schedule I saw, it was on there. And they canceled memories in the spring. So I don't know what's going on. Yeah, I love my Hot Wheels.
Do they know they're different?
Do they know they're different? I don't know. That is an amazing question.
Really hope so, because the only 490 many people can take.
Is memories?
Oh yeah, because I'm taking this first.
Oh, okay. Oh, you mean, okay. Yeah.
I took embedded last fall. So.
Oh, okay, yeah. So talk to send an email to Dr. Winfrey and tell him how important memories is, because you want to work for Micron, and Brian Calloway told you that this is the most important class you can take or something like that. Yeah, just, and it is, there are a lot of NAU grads that end up working at Micron, and because they understand the Micron terminology and the circuitry inside there, they're able to pick things up much quicker. It's extremely helpful.
Well, they don't seem to be hiring at the moment because they weren't at the career fair.
They did hire a few interns for the summer, but you just had to go in through the website and do it that way.
Oh, okay.
They will be hiring. I mean, they are doing fairly well right now because people need big memories to support all the videos we're uploading to Zoom. I mean, it's just IT in general is, I've got my stock portfolio. I bought a big chunk of just an IT services mutual fund, just because I figured people would be stupid using computers and that would continue on forever and just get worse. And it is amazing how much that one has exploded. Has made a lot of money for me. Also, railroads. That was another one. BNSF, I cleaned up on that one. What? Well, BNSF got bought out by somebody because they actually had the foresight to put in a second mainline track before, as gas prices were going up across the continent. And so they've kind of cleaned up on that, and then somebody bought them.
Oh, so this is a while back.
Yeah, that was a while back.
Well,
Yeah. It makes sense to invest in things that can make money. That is his thing. You invest in companies that can make money, not just invest in things that you think are going to go up. Okay, long-term strategies. Okay, so we're looking at frequency response. What we did last class is we looked at those decoupling capacitors on the board that purposely kill the low frequency response to get rid of undesirable things like 1/F noise. Mid-band was all the stuff we were doing before exam 2, or calculating the voltage gain, the input resistance, and the output resistance. Now we're going to look at things that slow transistors down. We're going to look at that high frequency band and what limits how fast MOSFETs can respond. And we're doing this from our linear model, which is a circuit model, which is based on the device physics. And we'll get to the Miller effect today, the dreaded Miller effect. It makes so much more sense than what I got when I was in college. And I just talked about this. The small femtofarad capacitors inside the transistor are what's going to kill my high frequency response. We'll get through the common source amplifier today. We'll beat that one to death, and then we'll quickly go through common drain. The common drain is also known as a source follower, and I think that's what they call it in the Cedra Smith book, if you want to know what's going on there. That came up. So here's our high frequency model. Again, it's a simplified version of what we think is going on inside there. There's a lot of capacitors in here. The ones that are due to the gate oxide are the gate to source capacitance and the gate to drain capacitance. We can't get rid of those. The source to body and the drain to body are not quite as big, so sometimes we can neglect those. Now, the wonderful thing about, and also the evil thing about the common source amplifier, the source and the body are generally connected together, because we're going to, and if the source and the body are tied together, then I've shorted out CSB so it can go away, and I've put that capacitor is now in parallel with everything else we've got there. So that is the next slide. This is the general model. The common source gets rid of this transistor and puts the drain to body in parallel with the rest. Would be a fairly straightforward circuit to analyze if it wasn't for this annoying capacitor right there, gate to drain. What I'm going to do here is I'm going to do a little circuit trick to move the gate to drain capacitor into its effective capacitance that is between the gate and the source, and another effective capacitance between the drain and the source. And then suddenly this becomes an all parallel circuit, and the analysis gets to be a little bit easier. That is what we're going to do when we start talking about the Miller effect. Okay, that oxide capacitance, not only do I have all these capacitors in here with the weird impedance 1/SC, but it changes, the value of these capacitors changes with voltage, and it changes significantly with operating region. So if I go into cutoff, my CGS is really small and my CGD is really small, and all the capacitance is between the gate and the body. This is the WLCOX, is the capacitance of that MOS capacitor, the metal oxide semiconductor. If I go into saturation, most of the capacitance gets lumped into CGS. This is the big part of it. And the COB is a very small capacitor. And if I go into triode, the capacitance gets split between the gate and the source and the gate and the drain. Circuit analysis programs like Multisim and Mentor Graphics and Cadence take this into account when they're calculating your particular, what's going on with your particular transistor. So you don't have to, thank goodness. And I'm back into that mode. Okay. So we go and we look at the Cedar-Smith book, and we look up the formula for the unity gain frequency. This is the frequency where the gain goes to 1 or 0 dB. This is also going to be defined as the gain bandwidth product later. And we look up this formula, and it says for this particular circuit configuration, the high frequency gain is going to be GM over 2 pi CGS plus CGD. Now, it looks straightforward to calculate. We know what GM is. CGS is 2/3 COXW over L plus the overlap capacitance. And CGD is the overlap capacitance. So we have to go through and calculate all those, or let Mentor Graphics do it for us. And we have to look up these parameters. These are what we call the SPICE deck. They're listed for a particular transistor or a particular process, a particular transistor in that process, and they give you all the values that you need to plug into that formula. So the first thing you would have to do when doing this is calculate this value, and this is just straight plug and chug. Calculate this value. Let's figure out what the numbers are just so we can kind of ballpark them in our heads. I'm not going to do the calculation. The calculation is in the slide solutions. I don't have enough time to do that. We're on number 12. CGD is 1.54 femtofarads. It's really small. It's just the overlap capacitance. And CGS is the larger capacitance. It's 6.18 femtofarads. So you're expecting femtofarads for most of these answers. And when I plug it into this formula, I get a whoppingly big 16.5 gigahertz. Doesn't seem like we have a problem. This is well into the RF band, past most of our major transmission standards. It looks like this thing works pretty good. Okay, then we'll get through the reality of this. Calculating those capacitances is a big, you may have to do this on the homework, I don't know, is a big equation. And a lot of this is based upon a model of what's going on. Some of these things like MJSW and MJ, they don't really complete, the physics is based upon the impurities, and it's very touchy, so they just basically measure them. I call them fudge factors, but they're listed down here. They're given. They have no units. Most people don't have trouble making this calculation other than the fact that it's tedious, except for one thing. There's this one term in this equation, and it just says VPN. And you're sitting there going, okay, I don't have VPN anywhere in any of these numbers. And what VPN is the voltage that you're putting across the diode. So this is the drain to body diode and the source to body diode. And you have to have that in order to do the calculation. My VPN is the voltage across the PN junction. So this is VPN. So you have to be given that in order to do that. Otherwise, it's just plugging in numbers. How do you calculate it with a lot of work? And that calculate if you care about it, if it does show up on the homework, when you do that, go back, look at the slide, and if you're having trouble with it, look at my calculation in the slide solution, and you can probably figure it out if you know what VPN is. That's what took me the longest to figure it out the first time. Okay. Now we want to look at the high frequency model of this thing. So remember, at high frequencies, these capacitors are large enough we can treat them like they're shorts, all three of them. The other thing we're going to do to draw our AC circuit is we're going to ground or deactivate our DC sources. So my voltage source becomes shorted out. It goes to ground. My current source becomes an open, so it just goes away. And I have a short to ground on the source. So when I'm taking my high frequency model and trying to figure out what it's doing in this circuit, my source is shorted to ground because it's through that CS capacitor. My gate sees V sig, R sig is in series, and we'll get to all the primes today, isn't that wonderful? And RG. And my drain sees RD in parallel with RL both going to ground, which is actually tied back to the source. So I can just do this, RD in parallel with RL. And there is the high frequency model. Now, we don't want to analyze that by hand, especially since all of these capacitors change with voltage, as we just saw in the last slide. They depend upon BPN. So capacitors are changing with voltage. Okay, we're going to do a circuit trick kind of interlude here. I have a capacitor, and the capacitor is going between V1 and V2, and I want to figure out what I is. Well, we know that I is, what is it? V equals IR. So this is going to be V over ZC. The impedance, my voltage in this case, is the drop is V1 minus V2, because this is the positive side. I'm doing passive sign convention. And ZC is 1 over SC. So I could flip the SC over and put it on the top, and I would get SC times V1 minus V2. Now, if we look at the special case, like you see in an amplifier, when the voltage on the drain side is the gain times the voltage on the source side. My V1 minus V2 is going to be SC times V1 minus K V1. Or we could just write that as SC V1 times 1 minus K. Now this is equivalent, if I think about the source side, it's seeing a capacitor to ground, an equivalent capacitance to ground, like it's C times 1 minus K. Because I could get the equivalent amount of current flowing, I'd have the same amount of current flowing through here as if I flipped this one to ground and multiplied it by 1 minus K. Okay, now K for an amplifier, for a common source amplifier, is a large number, and it's also negative. So we don't get negative capacitance here. We get 1 minus negative big number becomes, I've just multiplied this capacitor by a large number. And I've effectively just killed the gain at high frequency. We'll get to that. This is like my least favorite day to teach in here, but we'll get through it. it's, yeah, I don't know why. So keep that idea in the back of your head. I can take capacitors that are here and flip it down into an equivalent capacitance there from the input side. We can do the same thing on the output side. Now we want to try to simplify this schematic as much as we can. This part's pretty straightforward. I've got this little thing here called RL prime, and RL prime is going to be the parallel combination of RO, RD, and RL. And once I put that one in there, I can replace those 3 resistors with 1 resistor. So when you're doing the homework, the next homework, yeah, it wasn't this homework, I looked at this homework already. When you're doing the next homework, when it asks you for RL, that's a completely different thing from RL prime. Refer back to these, and the textbook, it's got primes all over the place. This is the same notation they're using in the Cedra Smith book. Now my second simplification here is I'm going to take V-sig and I'm going to do a source transformation on it. So let's just look at this part of the circuit. If I do a source transformation, some current here, it would be V equals IR, so I equals V over R would be, the value of that would be V sig over R sig. And I put this one in parallel, and now R sig becomes in parallel with RG. So I have R sig in parallel with RG. I do one more source transformation to this, and I turn it back into a voltage source that is V sig over V sig over R sig times R sig parallel RG. And I have a single series resistor that is this value. So what I've done is I've taken this part and I've turned it into this by doing 2 source transformations. And I've simplified that input into something that looks like a low-pass filter. That's fairly straightforward. Now all I have to do is be able to calculate R sig prime, which is R sig parallel RG. And when you do the algebra here, R sig parallel RG divided by R sig, the R sig in the denominator will cancel out, and I get RG times RG plus R sig times V sig. This is called V sig prime. They're different. Okay. So I've simplified my model. I still have this pesky gate to drain capacitor here that we'll deal with a little bit later when we get to the Miller effect. Why do we have to solve this problem 5.4 ways, Dr. Brower? I do put a tribute to her and at the end of the 490 slides. None of this would have been possible without her, but I do grouse about her. She always thought exactly the opposite of the way I did. I'd write a node voltage equation, she'd come up with a negative of my node voltage equation.
Great minds.
Okay, so remember what we're going to have to do here. And a lot of this we did before exam 2. When we're talking about amplifiers in the pre-exam 2 days, we did a DC analysis to find ID, VGS, and VOB. We calculated GM and R naught so we could stick them in our model. Then we calculated the midband gain, generally related to GM-RO, or maybe the negative of that. The next 2 steps are the things we've done since the last exam. If I have these coupling capacitors on the board, I can calculate the low frequency response using the methods we used on Thursday. And then the next thing is I want to be able to calculate FH due to the transistor capacitance. We get to do this 4 different ways today. We want to calculate the frequency response of this. There are several different strategies that people have used. Some of them are simpler than others, and some of them give you a little bit more insight into what's going on. Okay. So here, our input on this amplifier comes off of B sig, goes through R sig, has to go through CC1, goes from the gate to the drain, and then out here to get to V out. Now we look at this on the small signal model, we have to go through R sig. Some of my signal, to get to the drain, some of my signal could just go through this gate to drain capacitance and get out that way. Some of my signal may go and get charge up this capacitor, then that's VGS, then affect this current source, GM-VGS, and then get to the output this way. So I've got 2 different paths here through the small signal model to get to the output. That's another reason why I'm going to take that pesky capacitor CGD and flip it down so it looks more like a normal thing. Okay. Why did I not delete that? There aren't really any capacitors in series or parallel here, so we can't really combine anything. So I have to find what I have to do here, if I really want to do this right, is I look at CGS. I want to find its Thevenin equivalent with all the other capacitors out of the circuit and deactivating these sources. And leaving that one in as necessary. Then I would have to turn around and do it for CGD. I can't combine any of those capacitors. What? It's not. This is why there's 4 different ways to do it. The frequencies that affect FL are the capacitors we can see on the schematic. The ones that affect FH are these inside of here. So I'm going to get 2 different poles for those 2 different capacitors, or possibly zeros associated with them. I never understood why that slide was here, but transfer to the next slide. I was going to say, if you don't want to go through this, you just have to transfer. if you want to get out of NAU, you have to endure this next lecture. I call it the OCD method sometimes. So what I can do here, if I take, remember where CGD was? It's up here. I'm going to use that little circuit trick I showed you a while back, several slides ago, and I'm going to split it into 2 different capacitors. The effective capacitance, capacitive load we have on the gate, oh, that's an eraser. That's why it isn't writing. With the gate relative to ground, and another capacitor, which is the effective capacitance looking from the drain to ground. And I get rid of this one entirely. Then the circuit becomes somewhat easier to analyze. And they went ahead and jumped ahead and did that on this slide. So CEQ is going to be my gate to drain capacitance times 1 minus K. My gain of this amplifier is whatever my big RO is, which is RL prime, times GM, that's my GMRO, times a negative number. That is my K. So CGD times 1 minus K is CGD times 1 plus GM RL prime. So that is the equivalent of the gate to drain capacitance right there. I see confused looks. I'm not surprised. Okay. That's the CEQ as Cedra has it. Now it's in parallel with CGS. Parallel capacitors add, so I could just create this supercapacitor called CN, which is CGS plus CEQ. And then I have something that looks like this. Okay, it's just an RC low pass filter. That's not too terribly hard to analyze. Okay. On the output, I haven't done that yet. Okay. Yes, this is a low pass filter. The pole associated with a low pass filter, these are one of the things that you want to get to be automatic, is going to be, the frequency is going to be 1 over 2 pi RC. So I find this C. Which C am I going to use? I'm going to use the total combined capacitance CN, and the R I'm going to use is R sig prime. That will give me 1 pole. The amazing thing after we get done with the next 47 slides, or however many it is, on this, is that this is going to be the dominant pole, because CN is CGD multiplied by a very big number. So I have a high capacitance, I'm going to have a lower frequency. This is the one that's going to dominate everything. Yes?
Sorry, random question, but what is the difference between R-sig and R-sig prime again?
R-sig prime is R-sig in parallel with RG.
Oh.
Yeah. And that's back a couple of slides ago. Okay. Now, if we want to calculate FH, what I'm going to do, I've got RG, I've got CN. That's like the key formula to remember, even for like the final exam. So my FH is 1 over 2 pi RC. In this case, the R I care about is R sig prime, and the C I care about is my CN. I'm given CN, thank goodness I don't have to calculate it because it's a big long formula. My RG and R sig, let's see the effect of R sig on this. If I want to find R sig prime, it is RG in parallel with R sig. If R sig is 5 k ohms, 5 k ohms in parallel with RG is going to be a little less than 5 kilo ohms. No way to get around that. 18, what is it going to be? It's going to be 4.99 k ohms. Good guess. If I put 4.7 meg in parallel with 200K, I'm going to get a little less than 200K, and the exact value comes out to be 192 k ohms. Now, let's look at what happens to FH. So FH, we'll call this 5, is 1 over 2 pi times 4.99 times my input capacitance is fixed, 5 puff. If I put a 5K ohm resistor there, I get a bandwidth of 6.38 megahertz. I do the same calculation with a 200K signal source resistance, and I get 166 kilohertz. So the value that I have on my signal source is going to greatly affect the gain. And that corresponds to basically the output resistance of my signal source generator. So I need to have, as usual, you want a good low output resistance on my signal source generator to keep from killing the gain at high bandwidth. It is expensive to do that. You've got to build a better, source. And it's going to take up more room. You've got to make sure you get that common drain buffer output stage on whatever your signal source is to get the output resistance down as far as you can. And in CMOS, getting it down to 5K is, it's a task. So it's highly dependent upon how good of a source you have. A lot of times people don't think about that when they're first learning analog engineering or even just hooking up Arduino's ADCs into the real world and DACs into the real world, is that you've got to think about, like that homework problem that we did today, you've got to think about what is the output resistance of this and what is the input resistance, and am I going to get my signal in, and what is the capacitance I'm driving, and is it going to kill my bandwidth? I'm trying to train somebody to do analog engineering right now, so I'm thinking about it. I mean, we actually do it, not just talk about it in class. I have a meeting with him on Thursday. So the common source has really high input capacitance because CGD gets multiplied by 1 minus K, 1 plus GM RO. And in this case, RO is my RL prime. So let's just change that. High capacitance, 1 over 2 pi RC. I put a big number in the denominator. I've killed my bandwidth. This is one reason why BJTs are actually sometimes better than MOSFETs. I would have never admitted this a couple of years ago. Is basically BJTs have better frequency response, but you can get relatively high MOSFET frequency responses now. They're just not changing much. We're hitting the Miller effect wall. People were trying to push that limit for a long time, and they've kind of given up and just gone to other devices.
So, one question about
yeah.
The Miller effect. Is that GMRO prime or GMRO?
It's GMRO, big RO, and our big RO of this amplifier is RL prime. Oh. Yeah. Okay. Yay. Useful analysis tools. Okay, we're going to look at all these different ways to analyze this. Ultimately what we want to be able to calculate is, where is the frequency starting to roll off? When can I no longer depend upon the mid-band gain being the actual gain of my amplifier? That is the task before us. So there's our high frequency model. This is an amazing slide for looking back to and referring to when you're doing the homework, because it has, what the heck is R sig prime? You're going to forget it by the time you walk out of the class. What is CN? What is CL prime? And what is RL prime? The only thing we haven't talked about on this slide is what the heck is CL prime. It's whatever my load capacitance is, plus this gate to drain capacitor gets split here. It also has a portion that is seen by the drain. Okay, there's only one person that could have been. Okay. This was a student. Okay. And the portion that will get split there, it actually goes, it becomes 1 over 1 minus 1 over K as seen from the drain end. So this becomes 1 plus 1 over GMRL. That's a small number. So C on the output, CGD does not get multiplied by a big number. So I'm expecting this input to dominate the high frequency response, and it actually does. But, and we'll do this 4 different ways, and I think we come up with the same number. I'm sorry. This is why I don't like doing this. Okay, now the ways we're gonna actually try to estimate the high frequency gain. The easiest one is, okay, CL is not going to be nearly as big as the input capacitance because the input's capacitance got multiplied. So Miller said, let's just neglect that one and look at the frequency response of the input. That's fairly simple. We've already done that one. 1 over 2 pi r sig prime times CL. No prime. Okay. Then there's Miller's theorem, where I'm going to look at both this is the input only. I'm going to use Miller's theorem where I look at both the input and the output using that capacitive splitting and determine the effect of both poles. I get a better approximation that way. Then we're going to use the OCD method, OCT, to come up with something that doesn't require us flipping the capacitor over to convince us that we were in the ballpark flipping the capacitor over. And then finally, we will do an exact analysis that we don't actually do. I just say possible and explain to you how it's done. And what we find there is the results of these two are almost exactly the same. A better way, of course, since a lot of these capacitors are voltage dependent, operating region dependent, is to simulate it and measure it. And then you measure it in the lab. But the problem with simulation is you don't get any insight into what's killing your frequency response. If you're the designer and you want to build a better transistor, you have to get a handle on what's causing it to get worse so you can make it better.
This is simulation. These ways to estimate are in order from like the least accurate to the most accurate.
They all come out with almost the same number. We'll start a chart up here on the board. I can use my markers. I will just. We'll do the chart on the board thing. I have to do the chart on the board thing. We'll see what the numbers are for each one of these. The only one that really is badly inaccurate is the Miller's approximation. So here is the tabulation of the results. Miller's approximation, this is probably referenced to the 6th edition, but it's in the textbook. I saw it in the 7th edition today or so. FH is 1 over 2 pi Cn r sig prime. We've already gotten to that one. Miller's theorem takes into, oh, don't write in that one like pencil. Takes into account both the input pole, this one right here, it's the same thing, and the effect of the load capacitance. So that would be CL prime, RL prime. And then takes the geometric mean of the two frequencies and gets the total overall, whatchamacallit, frequency response. Now with the OCD method, what we're going to do instead of, remember RC is just a time constant, tau. What we're going to do here is we're going to find the total time constant by adding the initial time constant plus the time constant due to CGD plus the time constant due to CL. We add all these time constants together, and the total frequency response is just 1 over 2 pi times that total tau. The exact method, you get to throw in a 0. You get an FH1. You get an FH2. Equation 995 is a very long equation that you don't want to see. But in general, this is going to come out to be roughly the same by the time you get done with this. If you look at this, this is CGS times R sig prime. Well, we got that right here, CGS times R sig prime. CGD times 1 plus GMRL, we got that piece of it right there. And we have CL plus CGD times RL prime, and I swear this one's missing a prime for that one. It's the same equation, just a slightly different form. And with the addition of the 0. I don't know. But it would have to, there would have to be a prime there. Yeah. Now, how long it's been since I've read the textbook. I only read it when I need to. I haven't needed to for a while. If I have this CGD, I'm going to split it into 2 equivalent capacitors. One is seen from the gate to source, and this impedance here is going to be, oh, I'm going to really have to mess with you guys on this one. This equivalent impedance here, CGD, it's, if we do it as let's just do it as capacitance, because I won't mess with you guys. CGS times 1 minus K. And this one flips down and becomes, sorry, CGD. This one becomes CGD. Oh, great. Times, yeah, I got it. 1 minus 1 over K. Okay. I didn't want to do it in terms of impedance because it all ends up being upside down, and it just confuses people. Okay. So 2 different pieces of the capacitor. So I've got this CGD, I flipped it down, this becomes CN, and I've got an additional C2 right here. My C1 is CGD times 1 plus GMRL prime, 1 minus the gain. And this C2 is my new capacitor. It is CGD times 1 plus 1 over GM RL prime. Okay. We find FP1 at node G. It's 1. It's 1 over RC. 1 over 2 pi R prime sig C CN. That one's not too bad. We've done that one before. That's just the same one we got in the last result. So Fn is 1 over N2 pi Rn prime R sig prime, sorry, Cn. My output, if I deactivate this source goes to 0. My CGS, my VGS goes to 0. So this source goes to 0 too. What I see here is my output. It's 1 over 2 pi RC. You remember that part. I would be really proud of you. That's all I ask you on the final. RL prime, C out. And my C out would be, let's just put it down here, CL plus CGD D times 1 plus 1 over GMRL. And you can get to this really complicated formula using relatively simple concepts. It's just 1 over 2 pi RC. So we get the two formulas. And we get numbers for all these, and then we have to go calculate them. Okay, here's the kicker. This is the input, F, the pole at the input. It looks like a simple formula. 2 pi Cn r sig prime. But in order to do this, and you get to do this on the homework, I recommend at the beginning going through and calculating these 4 terms. Go ahead and calculate Cn, make it a number. Calculate r sig prime, make it a number. Calculate CL and RL, and then the rest of the calculations are straightforward. So do these first. Okay, 21. What do we get here? Oh, we got to this one right here. What the heck was this? Did we do that one? I wanted to get the number up there. 1 over 2 pi RC. Miller's theorem. What did we get? Sorry. I really wanted to do that. Well, we won't worry about it. Okay, so we wanted to get to R sig prime is going to be R sig in parallel with RG. You should know how to do that by now. 21 R sig prime is 100 k ohm in parallel with infinity because it's an open circuit, so this is just 100k. And I just use the numbers, this collection of numbers up here. RL prime is 500k in parallel with 250k in parallel with 10k. So that's a little less than 10k, 9.43k. And do those first because this RL prime shows up in the Cn equation. There's good order to do this in. Cn comes out to be 51.5 femtofarads. And CL prime comes out to be 106. So maybe there is a bigger effect here, 106.5 femtofarads. Then I calculate FP1 because I've got all the numbers I need for that. And FP, what the heck did I do? Did I really do that? Oh, FP1 is 30.9 megahertz. I said this is the one that would, the input one was the one that's going to kill you. My FP0, since my RL prime is a much smaller number, actually comes out to be lower. FP on the output is 158 megahertz. And, oh yeah, we got it here. Miller's, sorry, I need to do this. Approximation. The number we would have gotten for that is just my FPN, 30.9 megahertz. Miller's theorem is what we're doing right here. We're going to get 1 over, this formula right here, and FH comes out to be, how much does it change? 30.3 megahertz. So Miller's approximation wasn't too terribly bad. But it doesn't help you a lot if you're the designer trying to figure out how do I make this frequency response better. So let's go to the OCD method. Oh, I don't know how to do this. I'll do it. I'll just get out bamboo paper. Okay. What we're going to do, this is like an application of Thevenin. Yeah, I said that word. We're going to reduce V-sig to 0. It's like I'm finding the Thevenin equivalent that this capacitor sees. We're going to use superposition, so we're going to consider one capacitor at a time. All the others are open circuited, and we determine the small signal equivalent resistance that it sees. Now, CGS is really easy. V-sig 0, so this is going to go away. That's true on all of them. I'm going to take these capacitors and open them up, so they're not there. And I need to say what is the equivalence resistance that CGS sees. Well, the circuit looks like this. I can draw this one. This is like the slide from. This is like the worst slide of my. Never mind. Okay. R sig prime. This part's not bad. CGS. So there's the equivalent resistance that CGS sees. It's R sig prime. So there's one of them. CGS. R sig prime. Those are the two I multiply together to get that time constant. Now I have to erase, change colors, green. Okay, so now I want to look at CGD. So I open up this one. My source is still shorted out. I open up this one. Is this the horrible one? CGD. Oh, yes, it is. So my equivalent circuit looks like this. I've got to leave the dependent source in because I can have a VGS. I have this ground R sig prime. If I can get through this slide, I'm done for the semester. CGD is where we want to find the capacitance. So I'm going to I have to put a test source in. And I'm putting a test current source in, I test. Its equivalent resistance will be I test over V test, as we learned from Mr. Thevenin. And I've still got that dependent source in there, GM VGS. Okay, this is VGS right here. Okay, and that's going to ground. And I have RL prime. We want to analyze that. Yes, we really want to analyze that. I test the current going through here has got to be the same as the current going through the R sig prime resistor. So I'm going to just make it IT, is minus VGS over R sig prime. So that's one equation. But we really need V test over I test. So I can get another equation for I test by going this way and using KCL. The I test is the current going in. That has to equal GM VGS will be the current going through the dependent current source. And the current through RL prime is going to be, VG, oh great, VGS plus V test, it's already 5 o'clock, V test over RL prime. And we solve those two equations simultaneously. We get, just trust me, RL prime plus R sig prime times 1 plus GMRL. So that shows up, GMRL prime. That shows up again. So this is the resistance I'm going to have to multiply by CGD. Will be that resistance down there, RL prime plus R sig prime 1 plus GMRL. So that is big mess. I think the next one's not so bad. Okay. Yes. Let's change colors. Purple. We're doing a victory lap here. So basically, when I'm still get to disconnect this source, we want to find the oh, that's purple. We want to find the equivalent resistance this sees. If I disconnect this source now and this is open, there is this circuit, there's nothing driving it. VGS equals 0. And at VGS equals 0, GMVGS equals 0. So this puppy goes away too. So the equivalent resistance CL sees is RL prime. So I take the 3 time constants I get. My total time constant is going to be CGS R sig prime plus CL RL prime. Notice I skipped the one I don't like. Plus CGS times big mess. That's my total time constant. And my frequency, my F high is going to be 1 over 2 pi RC in the form of tau. So I find the time constant for each one of the capacitors, add them together, and I find the total H. How does this affect the answer? I feel like it's just downhill for the rest of the semester. There's my tau high. I don't want to go, and we calculated these numbers already, thank goodness. We plug them in, we calculate tau high, we find FH is 1 over 2 pi tau high. How does it affect our answer? This is number 23. Drum roll, please. 25.9 megahertz. Now that was worth doing. What have we found here? We found things that can kill my gain are not just this input node, this was Miller's approximation to only include these two. This one in the middle actually had a significant effect. Okay. That was method number 3. What did I say? Method number 4 today. Okay. Oh yeah, method number 4 is really easy to do because I just wave my hands. Okay, I told you it was downhill. When we do the exact analysis, we're going to get a 0 also. And we also get this really messy equation that Dr. Brower wouldn't even quote. Now, this is how we do the exact analysis. We're going to write node voltage equations. We're going to solve this circuit. No, we're not. We write the node voltage equation at the drain. So the sum of it's basically a KCL equation, right? The sum of the currents going in equals the sum of the currents going out. Check. We know how to do that. We write a loop equation or a KVL equation going around this loop right here. So V sig prime minus I n R sig prime minus whatever the current is going through the capacitor times its impedance. When we get around there, the voltage drops have to equal 0. Okay, we're okay with that. We write another node equation at the gate. So the current going in equals the current going out. We get a simultaneous system of 3 equations, and we can solve them. Aren't you glad I'm not doing that? And what we come up with is a transfer function that has an FH that is 1 over 2 pi tau h. The tau h, we've already argued, is exactly the same as it was with the OCD method. We get a 0 at GM over 2 pi CGD, and we get an enormously long equation, which is equation 995 in your book, which you don't really care about the result. Okay, which is, well, let me explain why. So what I've got here is I have FH, and FH is going to be the dominating pole. It's the one that kills the gain, and it will be at the lowest frequency. The 0 is going to be a GM 2 pi over CGD, is going to be at a much higher frequency. So when that 0 kicks in, your Bode plot, you got a minus 20 and a plus 20. It's going to cancel out and flattened out. And then we have a second high frequency pole that's even at a higher frequency that's going to cause the gain to roll off again. We just want these two to be separated by enough so that this value here is attenuated. It's below 0 dB. And as long as it's less than 0 dB, this thing's not going to tend to oscillate. Don't tell me how many mental... that just didn't... Yeah. Don't make me explain how I got there. Just keep your mouth shut at this point. Okay, we're almost done. What we get out of this, pretty much. Okay, so let's look at this. Tau H. If and this is the gain right here, this is K. If I increase the gain, I increase tau H, and I decrease the bandwidth. And it's almost like a universal law of engineering. Gain bandwidth product is a constant. Any op-amp, it's been proven for every, it's not a scientific proof, for every op-amp that's ever been built, the gain times the bandwidth equals a constant. If I want a really high gain, I need a really high bandwidth. Let's just go to the next slide, because that's what I'm talking about here. Yeah, it's a fundamental specification for all op-amps. A lot of times on the op-amp data sheet, it will not list what the bandwidth is. It lists what's the unity gain bandwidth. If I have a gain of 1, this is the bandwidth. If I have a gain of 10, my bandwidth is 10 times less than that. So you always have to take that into consideration. Now, this really happened with a capstone project about 4 or 5 years ago. Student comes in my office and says, I need an op-amp. It can just be any op-amp. It's good. I need just a slow op-amp. Which one do I use here? And the bandwidth doesn't matter. And I asked the kid, what's your gain? And he's like, it doesn't matter. I just need a low, like a 10 kilohertz bandwidth or something like that, or 1 kilohertz bandwidth. What is your gain? And he just kept on going on. And finally I get, what is your gain? And he goes, it's like 10,000. And if you need it, because it was a really small signal, if you need a gain of 10,000, you don't need a 1 kilohertz bandwidth op-amp. You need a 10 megahertz op-amp. So this is like the stuff that I deal with all the time, because nobody knows analog. No, you need a 10 megahertz op-amp. So keep that in mind. That's a really important thing to remember. Gain bandwidth is a constant. Again, this is a topic for 490 in the fall called engineer. It's like it's like the car talk of engineering. Click and clack, Julie, the engineering professor. Diving for data. Yeah, there's a lot of data sheet reading too, because part of your job as an engineer is to be an expert shopper. Can you pick the right thing that will work, that will cost 2 cents less or whatever? So when we go through and we calculate these, what do we come up with? Drum roll, please. FZ is 11.1 gigahertz. That's well out in the I don't care territory. FH1 is 25.9 megahertz. It's the same as the OCD method. I've just got the addition of that extra pole, and nobody bothered to calculate FH2 because it's so much bigger than FH1. So exact 25.9 megahertz. You've just got your first job as a test engineer at onsemi or TI down in Tucson, and they want you to go out and take this op amp and make it, or this amplifier, and make it a little bit better. How do you do that? Well, I decrease the gain. I got to make this number smaller to make FH bigger. We want to make this small. So I decrease the gain, which is usually not acceptable. I decrease that input resistance. That source resistance had a huge impact on that. Or I decrease RL, the load resistance, or the output capacitance. You get more of an idea of what you can do to fix this from that. Oh, thank goodness, we're almost done. This is what we did today. Presto, changeo. What we found, Miller's approximation, I'm looking at what I write on the board, 30.9 megahertz. It's probably good enough to put you in the ballpark. And it's simple. It's a calculation you can do almost in your head. Miller's theorem takes a little bit more work. I don't get much out of it. OCD, I get a much better. Exact, I get the same answer, 25.9. If I really want a good answer, I'm going to simulate it or actually build it and test it. But before you build it and test it, you want to go through this analysis so you don't build something that's a huge pile of garbage that everybody laughs at. You want to be in the ballpark at least, and maybe futzing with it a little bit to make it better at that point. Yeah, we're done. We have one more day of this, and then we can go into ACTs, ADCs, and DACs. Yeah, fun stuff. They kind of got some of this stuff from 380 got transferred in another level down to 286. So some of this will be review for you guys, but I will talk about some non-idealities of ADCs and DACs. The really basic ones, if you've been in 490, you've already seen some of these things like integral nonlinearity and differential nonlinearity. But we'll actually go through in the last homework and calculate those. And I had to do that. We had an ADC that we bought that was supposed to be super fast, super precise ADC we were using. And of course, my boss didn't believe the data sheet. This was Al Fowler. He didn't believe the data sheet. So he put me and a PhD from Bell Labs on the job of testing this. And the PhD he was a volunteer. The PhD, he was retired and bored and just came in to work with me. Okay. So put the two, he was a programmer and I built all the hardware and everything. We came up with a whole new algorithm for testing ADCs and measuring INO and DNO. And it was actually a pretty fun project. I like working with Heidelberger. He was a snowbird down in Tucson, so he'd show up on the doorstep of Kit Peak knocking, "Can I work with you guys? I'm bored."
You guys didn't have the DAC project in 286, did you? Because that's yeah.
Oh yeah, and it was you were in the weird semester. The semester nobody knew what they were doing.
Well, it's like after that point, Dr. S wanted to change it, so that way it was more representative of like an open-ended project.
Right.
Because project 3 is going to be like. So we had to build solo tracker by basically any means necessary.
Okay.
Oh,
Okay.
sorry.
I was the last semester for the EDC.
Oh, okay, so yeah, but we'll talk about that. And yeah, this guy actually used to program in a language called B.
Wow.
B.
That's a really-
It was what it was what existed before C that got developed into C.
The naming sense. So.
Yeah. Oh, I'm going. I think everybody was here except for Zach Hoover, Victor, and Chris. Oh, Chris Weber's here.
I'm here.
What's the problem with putting BJTs on a ski bus chair?
It can be done, but you need extra processing steps for that, and it costs money. It's just more money. The people who use BJTs regularly and JFETs and other type devices like that are working at Analog Devices or Maxim or some company who's building analog integrated circuits. CMOS is for the computer chips. So that's what Micron, that's what where a lot of people end up. Yeah, yeah. Victor, you're here too.
Still a tracker project, I remember I still put up.
Stop recording.
I thought we
Okay.
did so many things wrong and it was just the wires, like it was just the wires were loose and like the bad